Our next speaker is the Director of Science at the European Space Agency. Her specialties are studying supermassive black holes and galaxy evolution. But what I really like about her is that she is a strong advocate for equity in science. So please, it is my honor to welcome to the stage Carole Mundell.
So thank you so much. It's a huge privilege to join you here at this wonderful Starmus Festival. And in the next half an hour or so, I'm hoping to give you a whirlwind tour of our incredible cosmos, and in particular, the European component of how we've opened up new windows on the universe, and what we plan to do in the next decades, reaching out beyond the 2040s and 50s. So my background is I am an astrophysicist by background. I've been very privileged to work on some of the most exciting science possible. And latterly, I also spent time as the Chief Scientific Advisor and the Government Chief International Science Envoy in UK government, where I saw the real power of science for building relationships, for building friendships, and for peace around the world. And in particular, working in the Science Advisory Group for Emergencies and advising the Prime Minister during the COVID pandemic, the incredible mobilization of our science and technical workforce coming together to try to advise ministers at this time of global crisis. And so after I left government, I went back to academia. I rooted myself back in research. And I was wondering what I might do next. And this incredible role at the European Space Agency was advertised. It was not a role that I knew about. I had used data from European Space Agency satellites and also NASA satellites. And I'd also been an academic proposing for some of these missions. But I was not aware of the role of Director of Science. And so I read this job advert that combined science with engineering, with diplomacy, with management, and I thought, wow, this is my dream job. It must be made for somebody else. But I applied for it anyway, and I was hugely honored to be appointed by our Director General, Joseph Aschbacher, in December of 2022, and I took up post in the March of 23. And the reason that I mentioned 2022 is because it was a very important time for the European Space Agency. This photograph here is the 22 ministers from the member states who provide our budgets. And every 3 years, our ministers come together and we present a case for our budgets for the next 3 years. And they discuss what the right level of funding should be. And the reason that I love this photograph so much is because this ministerial conference in November of 2022 came at an immensely difficult time for Europe. It came just after the war in Ukraine had started. There was unprecedented inflation. And in fact, going into this ministerial conference, everything was a little bit uncertain. And the reason this is so inspiring is because these are 22 ministers. You may notice your own country's minister here. And they came together from all sorts of different political persuasions, all different kinds of countries with different sizes and different interests and different challenges. And together they discussed the future of space. And they gave us the biggest budget that we had had in the history of the agency. Our Director General, Joseph, is in the middle there. We had a 17% uplift on our budgets because all of these ministers decided that space is important for Europe. Space in all of its applications for the benefit of humanity should be invested in for the benefit of all of our citizens. And these were the values that really underpinned that ministerial conference. Through all of this leads world-class science. We do the best science, we have the brightest people, the brightest young minds coming through our universities, and we have some world-leading industries across all of our countries. Bringing all of that together with the biggest questions that we want to ask as humanity about the cosmos drives technological innovation. It helps our companies to grow and and develop brand new capabilities. But all of that has to be done with the lens of sustainability. And I know that, of course, the theme of this Starmus conference is Earth and the protection of this beautiful planet. There is no planet B. But through this talk today, I'll also show you how we're going to find out about other planets. And this is something that we now have at the heart of all of the work that we do in the agency. We have a zero debris charter, and we're talking about the sustainability of the planet. We did have a launcher crisis last year where we were moving from one type of launcher to another, and that's solved now because you need rockets to get into space to be a space agency. And of course, most important and last but not least is inspiration. The next generation, the youngest children who look up at the sky and ask those questions. When I give a presentation like this, it's always the youngest child who asks me the most difficult question about the nature of the universe, and that tells me that we've got a great future. So, as I say, the agency covers a huge range of different applications in space, all the way from looking down on Earth and studying how our planet is changing, whether that's for disaster prediction, whether that's understanding climate change, whether that's looking at the science of our oceans. And we have a world-leading Earth observation program. We also now have a strategy to clean up our own mess. We should not leave our satellites in space to crash into one another and produce debris. And we're now developing that technology to bring our rubbish home. And then, of course, we want to help our citizens connect, and connecting securely is very important. In the future, we're going to see a data revolution, and you all want your data to be safe, and when you're sharing your data with one another, it should be secure. So that was something else that our ministers decided was very important to invest in. And then, of course, as we look to the future of modern cities with potentially autonomous cars and how we live our future lives, space becomes critical in all of our everyday lives. But of course, it's not just on Earth. We're now starting to roll that technology out to our nearby neighbors. And there's a huge endeavor across the world to think about how we sustainably use, maybe even live on the moon. And we're very much centered on the Lunar Gateway. This is an international collaboration with our partners at NASA to ultimately send humans to the moon and potentially also to Mars. And this is a little rover that the UK in particular is leading that we hope will ultimately land on the surface of the planet and drill down and look for the signs of life. And I want you to hold on to that thought, the signs of life, because this is one of the big questions we ask as humanity. Are we alone in the universe? Has life existed elsewhere? And this is one of the big quests that drives our technology development. And I'm often asked what I think personally. Do I think there's life out there? And I think my first answer is it is profound if we find life elsewhere. And I think it will be equally profound if we don't find life out there. To be part of a living ecosystem in the cosmos or to be alone, I think really makes you reflect on the planet we have, on the lives we lead. And if you think about this on cosmic timescales, we are sentient beings for such a tiny fraction of the age of the cosmos. The universe is 13.9 billion years old. And here we sit today, alive and able to share this experience. But also as a species, we've been able to conceptualize the universe, discover the mathematics that governs and codes the physics of the universe, and then we've been able to develop the technology to test those laws of physics and actually go to other places in our cosmos. So as a human species, I think we are amazingly incredible and able to do remarkable things. And that, again, is something that I hope you will take away from this Starmus Festival. When we come together to do inspiring things, we really can do the impossible. So the ESA Science Program, of which I'm currently the director and the custodian, is world-leading. It's based on excellence. It's very, very highly competitive. If scientists come together and propose a mission, they're usually competing against 20 or 30 other teams. And so every mission, when we finally choose the mission and develop it, we know that it's going to be unique in the world. And over several years, we've now developed quite a comprehensive suite, and we do science that covers everything from near-Earth solar heliophysics, so just above our Earth's atmosphere, out through the solar system to other worlds, and ultimately to the nature of the fundamental nature of space-time. And I'll give you a taste of all of those. To do all of that, of course, we've, along the way, invented new technologies, novel design, engineering, systems, and the way people work together. Scientists across our European member state universities and research institutes, our engineers within ESA, and our industries across our countries. And it's really these novel designs and engineering capabilities that we're now transferring into those other applications, like the secure connectivity on the Earth or our lunar and Martian programs. And I wanted to show you this stunning movie. This is not artificial intelligence. This is actually the movie of the very first soft landing that humanity has ever achieved on a distant solar system object. And it was ESA's Huygens probe that went up with NASA's Cassini spacecraft. And it's landing on Titan, a moon of Saturn. And I think that's absolutely incredible. And if you look at the photograph in the bottom right-hand corner after the dust has cleared, these are not boulders. These are actually frozen chunks of methane on a frozen methane riverbed. And the fact that we could do that 20 years ago, I find utterly eye-watering. And shortly I'll show you we will be going back to Saturn. 10 years ago, of course, was the iconic and very eye-catching Rosetta mission. Many of you might have followed the fate of the little Philae lander. This was differently difficult. So the comet has very little gravity. You don't get attracted and pulled towards it. We actually had to do some very clever spacecraft driving in order to find this comet, orbit around it, and then stably land a lander on it. And this, you can see the movie, is actually the lander landing. And of course, as you know the fate, the lander landed slightly on the edge of a crater and toppled over and gradually lost power, didn't get enough sunlight, but did actually do some work before it finally went to sleep. And these images I just find are eye-watering. These are close-up photographs of another dusty world. And so we have this incredible story of innovation. We have a mission that has been now orbiting around Mars for the last 20 years. We've mapped the surface. We've found an awful lot of water on Mars. And so what we'll actually do is we will use these data to help our colleagues who are working on the ExoMars program to actually find the appropriate places to land, to search for life, and actually ultimately to use those resources for our astronauts. The other thing we're doing is we're very interested in moons of other planets, and this is the little moon of Mars. And this moon, Phobos, is very interesting because soon the Japanese Space Agency, in 2 years' time, will launch a probe, and the idea is actually to land on this moon. And of course, nobody's ever landed on a moon of Mars before, and so what we've done is we've used our Martian mission to actually go and take a lot of photographs of this little moon so that we can help our Japanese colleagues find the best and the safest landing site for their little probe. So you can see a story of international collaboration starting to develop here. And so overall, we have this incredible fleet of missions. In the bottom, you can see the missions that we've flown in the past. Those data from those missions are all available in our archives. In the middle, you can see the missions that we have flying at the moment. We have 18 different missions flying in the sky. And the ones at the top are the ones that are in development that we will launch soon. We've done the same for our cosmic explorers, so looking far beyond the solar system, we now have instruments in space that cover the entire electromagnetic spectrum of light, and we hope soon to go beyond that into the dark sector. And really, this is the instrument that we use. Physicists use light to be able to diagnose the physics of the distant universe. We understand how light works, we understand some of the physical processes that produces light at different colors, and we use the physics encoded in that light to try to understand how things work in the distant universe. And our missions are so well engineered that they last for a very long time. And you can see along the bottom the date, and the one on the bottom, of course, is the Hubble Space Telescope, and it celebrates its 34th birthday. It's been an iconic mission in collaboration with NASA, and really, to show that this engineering, particularly because Hubble had some vision problems when it first flew, you can see how engineers and scientists give their entire lifetime to conceiving, developing, building, and exploiting these incredible space missions. So it really is a profession of passion as well as challenge and precision. And we have had a fantastic year last year, and I'll show you some of the highlights from last year. But over the next decade and a half, we will launch a major science mission every 2 years, all the way to 2037. The work that I'm now doing as Director of Science is to plot what we do after that to make sure that Europe continues to have a world lead and builds on this incredible history of the last 50 years. So I said last year was a special year, and it was a special year for us. You may have seen some of these missions in the media. I hope you did. This is our very first L-class or large class flagship mission. It's called JUICE. It's the Jupiter Icy Moons Explorer. And we have a whole theme of cocktails going on, so you can actually make a Jupiter juice cocktail if you go to our websites. It's a phenomenal mission. It has 10 complex instruments on board, 85 square meters of solar panels. So we're using solar energy to drive the spacecraft. We launched it last year in April, and it's on its way now to Jupiter. The different kinds of instruments on board will be used to measure the environment in which the spacecraft flies. We'll take photographs and do remote sensing of the bodies that it flies past. And we'll also be doing some remote sensing as we go. And the big question that this mission is designed to answer is whether the icy moons in the Jovian system, which we think have icy crusts and we think underneath they have liquid, salty oceans, we want to understand whether there could be the conditions for life on these moons, in particular Ganymede, which is our final destination. And so the Jovian system is almost like a mini solar system. We can do all of the physics that we would like to study if we were aliens looking at the solar system. We can do that around Jupiter. So we will learn a huge amount about that system. We will search for those signs of habitability. But we will also use this as a planetary archetype for other planets and water worlds and gas giants in the rest of our solar system and beyond. And also on that bigger quest for habitable worlds beyond our solar system. Again, bringing you back to that question, are we alone in the universe, or do the conditions for life exist elsewhere? And finally, and last but not least, the environment around Jupiter is so extreme. There's lots of radiation, there are magnetic fields, there are charged particles zooming about. We can actually use it as an astrophysical analog for some of the most extreme places in the universe governed by black holes. So I went to the launch. Hands up, it's very bright in here, but hands up if anybody's been to a rocket launch. Oh, wow, there's a few of you. Keep your hands up if you didn't find it incredibly moving. I see no, now I see no hands up. Yeah, I can't describe the experience of watching this launch. And to really let you know how quite stressful it was as well, we had a 1-second launch window. And the day we were due to launch, 5 minutes before launch, the launch was scrubbed because we had a bad weather cell coming over. So lightning was coming over. So within 5 minutes, we stopped, which was fine. The team then took a rest. They then worked for the next 11 hours to come back the next day to do a launch with that 1-second time window on an Ariane 5 rocket. Our French colleagues had created that rocket for us. You can see the tunnel here with the dark brown smoke coming out. I actually stood in that tunnel. So the temperatures there during launch are about 1200 Celsius. You do not stand there when the launch is happening, obviously. Any of you who watch this online, I think there was a little photograph of a sloth. The sloth survived. It didn't get toasted. If you know what I'm talking about, you know. It was a wonderful launch. We launched in the 1-second window. And the reason that was important is because that spacecraft now has a very complicated trajectory, and we had to have all of the planets lined up just right. This is a photograph taken from the JUICE mission on its way out from Earth. I love the fact that it could take selfies of Earth. And this is really great for public engagement and showing people what we're doing. But it also has a really serious point. And it helps our engineers to understand how the spacecraft is performing. Everything was fine apart from one problem that we had with one of the antennas, the RIME antenna, which will sense the magnetic fields when we get to Jupiter. And you can see in this time lapse, this looped movie, that it's a bit like a fishing rod that was folded up and it had to spring out, and there was a pin that was stuck. And so our teams for several weeks shook the spacecraft, they heated the spacecraft up, all sorts of things you do not want to do with your very special spacecraft that you spent 20 years building. And eventually the pin became loose. Now you can see in the data plot here that obviously the thing went out, it locked into place, and it was safe. And we have the telemetry and we knew that. But actually for the engineers to see the thing unfolding and stably locking in place was a huge moment of satisfaction. So we were very pleased. And the satellite is now on its way. The other innovation here is that because we didn't have a rocket that was quite powerful enough to go directly to Jupiter, we had to do something very clever with all of the gravitational physics. And we'll do the very first gravitational slingshot between the Earth-Moon system later this year. We'll do a similar thing around Venus, and then we'll continue to do those slingshots until we get out to the Jupiter system and around the different moons. We'll take data as we go, and eventually in 2031, we'll make it out there, and we will eventually settle into an orbit around the moon of Ganymede. And because the launch was so perfect, we've saved enough propellant on the spacecraft to be able to do an extra loop of Ganymede, and instead of being 500 kilometers above the surface, we'll go down to 200 kilometers above the surface, which is incredible, before we finally end the mission on the surface of Ganymede. So our scientists are very excited about that. And if there are any young people in the audience, any school children in the audience, you might be the scientists who will work on the data that we gather from this mission, and you may find the signs of habitability. So we're very good at doing these sorts of flybys, but this mission that we've decided to build this year will really test the limitations of our ability to drive spacecraft. And this is the Envision mission to Venus. It will fly to Venus, and it will actually, for the first time, study everything from the upper atmosphere of Venus right down to the core of the planet. And in order to do that, we can't just fly straight there. We have to do a thing called aerobraking. So we'll have to go around the planet about 1,000 times, slowly using the drag force of the oxygen-rich environment to slow our spacecraft until it gets into orbit. So that's quite difficult. Oxygen's quite corrosive, so we need to have special materials so our spacecraft doesn't dissolve. And we also have to get the flight dynamics absolutely perfect. But of course, the big question we want to answer is, why is Venus, which is our twin sister planet, so different from Earth? And we hope to really understand how it became that way and make sure that we don't follow the same fate, because it's a pretty hot and unpleasant environment to live in. In order to practice these sorts of flybys, we already have a satellite, a spacecraft in flight called Bepi Colombo. Again, this is with our Japanese colleagues, and this launched in 2018, and it's on its way to Mercury. And every so often, we have to fly past Mercury. It doesn't have much of a gravitational pull because it's a small planet, much smaller than Jupiter. So it's actually quite a challenging thing to do, to kind of come to a skidding halt in the orbit of Mercury. This is one of the flybys we did in 2022. This is a real movie of us flying by Mercury. We gather data as we go, so the scientists are already studying this planet, and this is just a close-up of the high-gain antenna looking at Mercury. And the next few months to a year will be absolutely critical. What we're trying to do is get into a stable orbit in 2025, and then we have 2 other spacecraft on board that we will then launch from the orbit of Mercury to study the planet in more detail. So again, really pushing the frontiers of technology. And of course, the other thing about Mercury is it's very close to the sun, and it's very hot. It's been a bit described as flying a spacecraft into a pizza oven. So it's, again, very hostile, and we've had to create very special technology to do that. And using that technology, we then put that on another spacecraft called Solar Orbiter. And this is a very special mission. It's going very close to the sun, and it's studying the nature and the physics of the sun. And the reason that this is special is because we want to understand our nearest star. It has a big impact on us here at Earth. Again, hands up anybody who saw the aurora these past 2 weeks. Did anybody manage that? Yeah, fantastic. I didn't, from Spain, unfortunately. Now, the aurora are very beautiful, but actually they're also very serious, because these are charged particles that come from the sun during a time of activity. And those charged particles don't hit us on Earth, but they actually get trapped in our magnetic fields. And the light that is produced is the effect of those charged particles as they hit our Earth's atmosphere. Now, obviously, we have spacecraft in space, and we have an increasing number of spacecraft, so we really care about this so-called space weather, because it can have real negative impacts on our spacecraft. And actually, if you have a really big solar flare, it could, in principle, blow some of your electrical substations on the ground. So from civil security, we also really care about the physics of the sun. And what Solar Orbiter is meant to do is really help us to understand the sun, both in its active phases, but also in its normal phase. And this is actually a beautiful image series of images put together in a movie. 5 minutes of real time is about a second in this, and this really is the surface of the sun just burning along. You can see the loops of the particles going around the magnetic fields, the so-called coronal rain, and you'll see a little flare just pop up there. So this is happening all the time on the surface of our star. And the reason this mission is particularly special is, for the first time ever, we will go out of the plane of the solar system in which our planets orbit the sun, and we'll be able to see a view of the poles of the sun. So humanity has never, ever been able to study the poles of the sun, and we'll be able to understand how that couples to our Earth system. And so really what we now want to do, of course, taking all of this knowledge about our own solar system, is export that and understand other solar systems in the world. And so we're now going into a very exciting time for our agency, where we have a number of exoplanet missions that are in preparation. This mission, Plato, is a phenomenal piece of engineering. We have 26 cameras, exquisite sensitivity cameras, that we have to design and build, all to be identical with one another in labs across Europe. They then have to be integrated onto a single platform and then flown into space to act as one single camera. And the purpose of this mission is to look at Earth-like planets around Sun-like stars. So we're literally looking for analogues of our own planet around analogues of our own Sun, because we understand quite a lot about our solar system, but we're now going to do this for many other solar systems. And if you ask any astrophysicist who was working in the 1970s, 1980s, what do you think the chance of finding a planet around a star other than our own Sun is? I think they would unequivocally say 0. There's no chance we'll ever have the technology to do this. Fast forward now to 2026, and we will be out there looking for Earth-like planets around Sun-like stars. We think we've already found about 5,500 planets in total. A complementary mission that we'll launch a few years later is the Ariel spacecraft. And now we're really starting to dig into the properties of these planets. So Ariel is really special because we will study the atmospheric chemistry and thermal properties of 1,000 exoplanets. So we're now going to start to do climate studies of 1,000 other planets other than our own Earth. So if you think about how much we understand about our own Earth, all of our ESA satellites that look down on the Earth and understand climate change, we now will be able to do this with exoplanets orbiting around other stars. Suddenly, we put our planet into a cosmic context. And the other really exciting thing about Ariel is we have a little bit of space in the rocket, and so we've designed this innovative little mission called Comet Interceptor, and they will both launch together. And then once Ariel gets out to its destination, about 1.5 million kilometers away from Earth, it will then launch Comet Interceptor. Comet Interceptor itself is 3 spacecraft. Comet Interceptor will loiter in space for a few years. It will wait for a pristine comet to come by, a comet that has never been in the inner solar system before, but is a relic from the birth of the solar system. And it will then launch itself in space and chase this comet. And it will then also release 2 probes to study the comet. So again, we're testing these really complex technologies, but to try to answer some of the most fundamental scientific questions we have. And then putting all of that technology together, what we're now starting to think about is what mission we need to start to design now in order to be able to fly in the early 2040s. And building on our JUICE mission, our scientists have said we really want to go and test for life, not just the conditions for life, but actual life on a distant moon, a distant icy moon. And so we asked our experts to spend a couple of years trying to figure out what the best destination is. And we published this report a few weeks ago. So the answer is out. Our destination is Enceladus. This is a moon of Saturn. We know there is a plume of material that's pouring out of Enceladus, which is probably coming from the ocean beneath. Our scientists said to us, we would like to fly through the plume and test for life and prebiotic molecules, but actually that's not enough. We want you to figure out how to land on the moon and take some samples. And so that's what we're challenged to do. We think we have the technology. Some things we'll have to invent, and other things we will bring from our other missions. And we will probably use a few rockets. We'll probably launch our spacecraft. We'll probably launch our lander, and then we will probably assemble those in orbit around the Earth, and we will then fly those out with much bigger solar panels than JUICE has out to Saturn. That'll take a few years to get there, and then we will land and do our experiments. So we're very excited about that, and we hope that when our ministers come in 2025 and we ask them for an uplift in our budget, they will be equally excited about this mission to go and sample for life on a distant moon, and that they will support us in our ambition. Now, I've given you this great tour of all the planets in our solar system and what we're going to do, but that's only 5% of the entire universe. So to finish up, what I want to do is give you a whirlwind tour of the rest of the cosmos. So we understand less than 5% of the universe. We think from our Cosmology satellite Planck that the rest of the universe is made up of material called dark matter and dark energy. We know that the universe is expanding, but we don't know why it's accelerating that expansion. It goes beyond the laws of physics as laid down by Einstein. And so last year, as well as launching JUICE, a few months later, we launched this incredible mission called Euclid. And this is what we call our dark detective. So the idea of Euclid is that it will actually study the dark universe and help us to understand the nature of this expansion and how the universe first began and how it formed over the last 10 billion years to the current state that we're in today. We have some very special material that we've developed through many years in Europe. This is called silicon carbide. This is a material that's very stiff, and it's also thermally very stable. Because what's very important for Euclid is that it's incredibly sensitive, and that we don't want to measure the temperature of our spacecraft. We really want to be looking at the cosmos. We launched from Florida on a Falcon 9 rocket. It was a beautiful sunny day and just as good a launch as we had for JUICE. And the beauty of Euclid is that it's optimized for very wide field imaging and spectroscopy. This is a photograph from the Hubble Space Telescope. It's got hundreds of galaxies in there, but just with one shot from Euclid, you actually cover more than the size of 2.5 times the size of the Moon. And in one shot, we get 600 million pixels. And so this actually tells you that we can do a huge survey. We have very, very precise optics, so the sharpness of the images is exquisite, and the sensitivity is such that when we had a tiny little bit of ice on our optics, thinner than a strand of DNA, it caused us problems, and we had to de-ice. In November of 2023, we released the first images from this incredible mission to the world, and it had a huge reach. I believe there was even one of these photographs shown on a bus in Tokyo. They are absolutely exquisite, and our scientists have been mining them ever since. And if we zoom in here, you can start to see how beautiful and how powerful this mission is. This is a cluster of galaxies, about 1,000 galaxies pulled together by the force of gravity and hidden dark matter. We can zoom in and we can actually study the galaxies if we want to, or we can start to look at the background. And within this same image, we have about 100,000 galaxies reaching back 10 billion years in the rest of the cosmos. And that's just a single shot of the sky, and it took about an hour of data. It would actually take many, 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 many years for the James Webb Space Telescope to do this. People who care about galaxies can study them in great detail. This is a dwarf galaxy. These are the building blocks of galaxies, and we can even zoom in, and we can actually start to see new stars being formed in little stellar nurseries. We have a very famous stellar nursery in our own Milky Way galaxy called the Horsehead Nebula, and again, this was just a single shot from Euclid. So we've got all of this detailed information. You should look out next week, mark your calendars. We're about to release the next early science and the new images that we took at a special event next week in Spain. Actually, we will do that globally. And what this mission will actually do over the next 6.5 years is survey the entire extragalactic sky. 36% of the night sky will be surveyed autonomously with the mission. And what the cosmologists will do is they will measure very precisely the size and the shape of about 8 billion galaxies, and they'll pick the best 1.5 billion of those to try to map out the structure, the nature of dark matter, how it couples with dark energy, and how that's driving the expansion of our universe. And I always like to give this number. So we will end up with 1.5 billion galaxies. Mission cost in total that we paid into European industry was about 1.4 billion euros. So that's about 90 cents a galaxy. I think that's quite good value. Now, you're asking about the rest of the sky, so we'll do 36% of the sky. The rest of the sky is dominated by the Milky Way, the galaxy in which we live, and when we look up on a dark night, you'll see that dusty band across the sky. That's our Milky Way galaxy. And there's a zodiacal light that comes from our own solar system. And a mission that we launched back in 2013 called Gaia has mapped all of that. So we did 2 billion stars in our own Milky Way galaxy, and we wanted really to understand how the Milky Way formed. It's our home galaxy. It's a wonderful collaboration of 450 people from 25 countries, and they help us to analyze these data, find these new objects, and publish that information to the rest of the global science community. So this mission has been very, very impactful. Now, you may have seen this before. This is not a photograph. This is actually a dot-to-dot picture. Every single pixel in this image is a star for which we have measured the distance, the brightness, the position, how it's moving, and where it's come from. So we've now actually built up an entire evolutionary history of how our Milky Way galaxy came to form. And in doing so, and looking to see how the stars move, and maybe looking at some of the stars that move in a way that we think they shouldn't, we've already found 3 new stellar mass black holes. We know there's a supermassive black hole at the center of the galaxy, but we didn't know that the galaxy has free-floating black holes. And this is actually really starting to challenge our understanding of star formation and how black holes form. So the biggest one that we found most recently is 33 times the mass of our sun. We don't know how to produce a 33 solar mass black hole just from the collapse of an ordinary star, so things must be colliding within our Milky Way. And the reason this is exciting, apart from finding new black holes that we didn't know existed, those black holes will actually act as cosmic calibrators for our next really important fundamental physics mission after Euclid. This is called LISA. Is what's called the Gravitational Wave Interferometer. There is one on the Earth in the US and across over to Japan and to to Europe. This will be the first ever space-based interferometer. So we will launch 3 identical spacecraft out to the Earth's orbit, and they will fly in a triangle, a perfect triangle. And that triangle will rotate as it goes around the sun. It's on an Earth orbit. It will be almost rigid. We'll have to do very little extra orbit control, and it will act as one single instrument. And the distance between each of those spacecraft is about 2.5 million kilometers, and there are lasers shining from each spacecraft to keep the spacecraft in sync, and they will have to be aligned more precisely than a picometer. So you can see what an incredible set of technology we have to develop. And the reason we have this interferometer is when space-time stretches and wiggles because of ripples in space-time and supermassive black holes collide, these spacecraft have test masses on them, and each test mass has to not know it's flying on a spacecraft, and when the test mass wiggles a little bit as a gravitational wave passes by, that's how we'll know we've actually sampled ripples in space-time. So it's almost like a science fiction mission, but it's science fact, and we're just putting the contracts out to industry at the moment. And again, another huge international collaboration and cooperation with scientists, engineers, and industry across Europe, and also with our friends at NASA. And then to end this fast whirlwind tour of the universe, I wanted to take you to the hottest parts of the universe. So we'll now be sampling the nature of space-time itself, but half of the known material in the universe is hotter than 1 million degrees, and we don't know why. These are the most extreme regions in space, often associated with black holes. And we had 2 other missions that we launched with partners this year. Einstein Probe was with our Chinese collaborators. This is a high-energy mission that will detect X-rays from the cosmos, but will be very agile and will look for new flashes of X-rays on the sky when new black holes are born. GRISM is a mission with our Japanese colleagues, and again, that's in the high-energy X-rays, but now looking at the spectra, so actually looking at atoms, and when atoms change and emit lines, we can actually do some cosmic chemistry. This was our first light spectrum from our Japanese colleagues. You can see the gray trace in the top was the old spectrum, the best state of the art, and underneath in the white trace, you can see the exquisite detail. So we can see silicon, we can see sulfur, argon, calcium, iron, all at high-energy X-rays. So now we're starting to do X-ray chemistry in the cosmos. And these missions are actually pathfinders for the next big X-ray observatory. So we are doing the technology development for this amazing X-ray mission called New Athena. It will launch in 2037. So when LISA launches in 2035, it will take about 2 years to get out to its orbit and form its triangle. And as it reaches its destination and starts to operate, we will launch New Athena. So we will then be sampling the ripples in space-time and the hottest material around accreting black holes altogether. So we will have this incredible complete view of some of the most extreme unknown physics in the cosmos. And just to finish, you are all able and welcome to come and dig into our archives. We do lots of programs with school teachers, with international school teacher networks, with pupils, with students who come to visit us in Spain and also in Paris and in the Netherlands. And we actually serve about 120 terabytes of data to over 34,000 users every month. And we're constantly updating our tools so that you can mine the planetary and the cosmology and the astrophysics archives, and you can start to bring them together. We we had one brilliant young woman who came on an archive fellowship, and she said, I'd like to use your Planck cosmology data. So this was the mission that looked at the dying embers of the Big Bang for us and helped us to figure out that we don't understand 95% of the universe. And we said, sure, what kind of cosmology question would you like to ask and answer? And she said, oh, I'm not going to do cosmology with it. I'm going to use it to look for all the metal asteroids in the solar system. We were like, wow, who knew it could do that? And so these missions are so innovative in the way we design them. They deliver the core science, but then new generations of young scientists come in with brand new questions, and through our archives are able to do completely new science that we could not possibly have imagined or envisaged would have been possible when we designed the missions in the first place. So we've had 50 years. In 2025, we'll be at our 50th anniversary, and I really hope you'll be with us on our journey to the next 50 years of cosmic discovery, collaboration, and friendship. Thank you very much.